Welcome. This video is going to take a look at some of the trends or periodicity that we see on the periodic table. And because the elements are arranged by atomic number, that means they're also arranged by their total number of electrons. Remember, atomic number is defined as the number of protons, and since an atom has to be neutral, that will also be its number of electrons. So for each row, the period number lets you know the number, the outermost energy level for those elements. So what's the largest energy level that that element has electrons placed in? And as you move from one element to the next across the periods, then the number of valence electrons increases by 1, at least for the representative elements or for the A groups. So that means group 8A elements or group 18 elements have 8 valence electrons in their outermost energy level. That means they have a full s and a full p orbital for whatever energy level is their outermost or biggest. Except for helium, which only has 2 electrons because it only has the first energy level with just that one s orbital. And for some reason, this makes noble gases super unreactive, or what we consider as very stable. For group A families, or the representative elements, and the group number is going to be equal to the number of valence electrons. So 1A has 1, 2A has 2, etc. For the B families, the transition metals, remember, they're all filling up a D or an F orbital, and that's always 1 or 2 levels back or below the current energy level. So that means they also have 2 valence electrons. But because they have that D or F orbital, they can move electrons between those orbitals. So sometimes they have different valence electrons or do different things than what the representative elements do. So elements in the same group tend to have similar chemical properties, and that's because they have the same number of valence electrons. No coincidence. So this is just a chart reminding you that on the left side, a lot of purple there, those are the metals, the darker purple being transition metals. The green is showing you the metalloids, and then the yellow is showing you the nonmetals, and that includes hydrogen over in group 1A. So hydrogen is kind of weird in that it belongs in group 1A because it only has 1 electron like the rest of the 1As, but it is not an alkali metal. The transition elements and the B group elements, they fill their outermost shell as well as going back and filling an inner D or an inner F orbital. So again, this allows transition metals to move electrons between the D or F orbital and the outer energy level. So it can change the number of valence electrons. Sometimes instead of 2, they slide 1 to the D orbital and only have 1. Other times they move electrons out of the D orbital and end up having 3, 4, 5. So typically 1, 2, or 3 are the common number of valence electrons, but it can be as high as 5. Example of this is copper. If you look at copper, it's number 29 in period 4. So its noble gas configuration is argon, 4s2, 3d9. And so if you think about this, this d orbital has 5 different orbitals, and 4 of them have 2 electrons, and 1 of them only has 1 electron. So I've got the s orbital looking like this, and then I've got this big d orbital, and 4 of them are full, and this last one looks like this. Well, copper often has a valence electron of just 1 that it gives up to become stable because 1 electron is donated in an ionic bond, and this other electron is often shifted over to fill up this d orbital. So that's one of the things that you can expect to happen with transition metals. And that's not something you'll be asked to predict. It's something you'll be notified of with the way we write formulas. So inner transition metals, and remember the ones placed below the main body of the table, and these are the ones that are filling up the F orbital, and these are actually very, very rare. In fact, if you look at the names, you probably haven't heard of most of these. That's because the first row, the lanthanids, are also called the rare earth because their natural abundance is less than 0.01%. Like, that's a crazy small amount. And then the actinides are all radioactive, and only 90, 91, and 92 even occur in nature. The rest are all man-made. So the intertransition elements, be aware of what those two rows are, but don't worry about them much beyond that.